Welcome back. In this video, I'm going to introduce a brief review of radicals and quadratic equations. And this is going to help us, or help you, as we continue our studies and head towards the Pythagorean theorem. Importantly, you will need to know and recognize your perfect squares. So I'm going to ask you to memorize your perfect squares up to 15, plus maybe a few more of those. So recall that 1 squared is 1, and therefore the square root of 1 is also 1. And 2 squared is 4, therefore the square root of 4 is 2, and so on. So you should know those all the way up to 10. And then a couple extra ones. 11 squared, it's 121. 12 squared, you should know that one, that's 144. So the square root of 144 is 12. A couple other things you'll need to be familiar with. The square root symbol is also known as the radical, and what is inside or underneath the square root is the radicand. So a little bit of vocab for you that you should be familiar with. Some other perfect squares you'll need to know and be familiar with would be 13 squared is 169, so the square root of 169 is 13. 14, 15, 16, know all those. 16 squared is 256, so the square root of 256 is 16. Should know the square root of 289, or you should also know 17 squared. And then 20 squared is 400, so the square root of 400 is 20. And you should also know things like, 30 squared is 900, so the square root of 900 is 30. You could also probably know 40 squared, that's going to be 1600, and so forth. And the other one, 25 squared, that'll come up every once in a while, is 625, so the square root of 625 is 25. And again, it'll help to memorize those. In simplifying a radical expression, so an expression has no equal sign, we're going to use the principle or the positive square root. Some of you may be thinking, well, square root's always plus or minus. We will get to that, yes. But right now we're going to work with just the principal square root. So certainly these are some principal square roots above that we've already covered that I'll expect you to be able to simplify. But there are some other ones that you'll also want to understand and learn the process of. So when simplifying square roots, we're going to want to look for the largest perfect square factor. So we want to seek the largest perfect square factor. And we have our perfect square factors listed above and committed to memory. So the square root of 48, you may recall from square roots that we can take the factors of those square roots. You could take the square root of 6 times the square root of 8, but there are no perfect square factors in there. So our highest perfect square factors that we want to use would be the square root of 16 times the square root of 3. So that is the equivalent of the square root of 48. If you're familiar with factoring trees, this will look familiar. Well, the square root of 16 is 4, and the square root of 3 is fully simplified, so the square root of 48 would simplify all the way to 4 square root of 3. We would do the same thing for 242. Hopefully you would see inside here the square root of 121 times the square root of 2, and you'd simplify that all the way to 11 square root of 2. Here we want to add some like square roots. We want to simplify this, but we can only add and subtract like radicals. So kind of like we can only add, 3x plus 4x is 7x, and we can't add 3x plus 4y does not equal 7xy. We would never do that because they're not like terms. Well, the same thing with square roots. So these aren't like square roots. It doesn't look like they can be added. But let's take a look a little more closely. They can be simplified. The square root of 18 can be simplified, just like we did above, to 3 square root of 2. And the square root of 32 can be simplified. That's the square root of 16 times the square root of 4 square root of 2. And the square root of 75, our perfect square factor in 75 is 25 and 3. So that is 5 square root of 3. Well, the square roots of 2 are like square roots, so they can be added. And we get 7 square root of 2 plus 5 square root of 3. The square root of 3 and the square root of 2 are not like square roots, so we're done. This would not equal, 12 square root of 15. That is totally incorrect. We can't add these because they're not like square roots. Another thing you'll have to do when we're working with the Pythagorean theorem is you'll need to be able to rationalize denominators. Okay, so we don't want any square roots, any radicals or cube roots or anything in the denominator. It's a formatting thing in mathematics. So the square root of 5 is the equivalent of the square root of 5 over the square root of 3. And we can rationalize that square root in the denominator. Well, every number multiplied by itself is its own perfect square. So if we multiply the denominator by the square root of 3, that's going to get rid of that square root in the denominator. But of course, if I multiply the denominator by the square root of 3, I have to multiply the numerator by the square root of 3. This is 1. Okay, so I keep the same location on the number line. Same location on the number line. So that is going to simplify to the square root of 15 all over 3. And that is my simplified answer. Now, you'll also be asked to solve radical equations. And here, when we're solving for x or we're solving for y, we have an equal sign. Now we're going to use the plus or minus. Okay? And here's an example of y. In this particular problem, if I subtract 25 from both sides, I get x squared minus 16. Give myself a little more room here. X squared minus 16 equals 0. Well, you may recognize this from your factoring days as a difference. Subtraction is difference of two perfect squares. So this is factorable. So that is factored to x minus 4 and x plus 4 equals 0. We set each of our factors equal to 0. We get x is 4 and x is negative 4. And can x be negative? Sure it can, all the time. Sometimes it may not make sense in the context of our problem, but it can always be negative. So let's take a look here. We got two values for x here, 4 and negative 4, and if I substitute back, you'll see that they'll both work. Let's try the same example, but looking at it a different way. If I subtracted 9 from both sides, I get x squared equals 16. Well, you probably know to undo x squared, we can simply square root both sides, and we can do that. And we'd say x equals 4. But if we don't do the plus or minus, we lose one of our solutions. So you can see here when we factor this as a difference of two squares, same problem, we get two different solutions. Well, that explains why we have to do the plus or minus. Now that won't always work, but it is going to work here again in this next example. I could look at subtracting 54, but that's not a perfect square. So for x squared equals 54, I'm going to take the square root of both sides. Put my plus or minus in right away. The square root of x squared is x. And we get plus or minus the square root of 54. Well, that's going to be plus or minus the square root of 9 times the square root of 6. So x equals plus or minus 3 square root of 6. Sample D is a little bit different. X squared plus 4x equals 12. Boy, I don't really want to subtract 4x and square root both sides because I don't want to take the square root of 4x. That's not going to be real friendly. So what I want to do here is I want to subtract 12 from both sides. So I get x squared plus 4x minus 12 equals 0. And now I'm going to have to factor this. So I'm looking for factors of negative 12 whose sum is a positive 4. Well, 6 times 2 is 12. And if I have a positive 6 and a negative 2, that'll give us a negative 12. And those are going to be my factors. But I also have to make sure I have factors of my x squared. We kind of take this for granted. Factors of x squared will always be x and x. And then if I do x plus 6 and x minus 2, if I FOIL this back, if I multiply this back, I would get my original trinomial here. And then I set each factor equal to 0, so I get x equals negative 6 and x equals 2. And that's my final answer. Those are my two options for x that will work. Finally, I have x squared equals 3 squared plus 4 squared. The common thing to do here is just to take the square root of both sides. Well, we have to be careful here. What I've done is not really correct. What we need to do is take the square root of the entire side. And I'll show you in a moment that the square root of 3 squared plus 4 squared is not equal to the square root of 3 squared plus the square root of 4 squared. So we have to treat this as a quantity. We have to treat that as a quantity and simplify inside the square root first, or under the radical first. Make sure you do that first. So the square root of x squared is going to be x, and we're going to do our plus or minus, and that's the square root of 9 plus 16. So x equals plus or minus the square root of 25, and x equals plus or minus 5. Doing this the incorrect way, just for an example, we'll say this. We'll say the square root of 3 squared plus 4 squared does not equal the square root of 3 squared plus 4 squared. We saw that this is the square root of 25 does not equal 3 plus 4. Because when we square root these individually, the square root and the square are inverse operations. They cancel each other out. And we get 3 plus 4, and we get 5 equals 7. Well, we know that's not true. So we can see here that this method is not correct. We cannot do that. We can't split those into their own separate square roots when we're adding. We can do it when we're multiplying, as we saw earlier, but not when we're adding and not when we're subtracting. So there's your introduction to radicals for geometry, and we'll work on this more when I see you in class.